Hi, my name is Julia Silke, and I am a data scientist and software engineer at our studio. And today in this video, we are going to use data from this week's Tidy Tuesday on climbing expeditions in the Himalayas, like climbing Mount Everest and similar peaks. And we're going to train a model using tidy models to be able to try to predict who survived these expeditions and who died. We're going to be able to show how to approach modeling tasks like imputation and how to deal with class imbalance when we do our feature engineering. So this is a pretty interesting data set, so I'm excited to get started.
All right, let's get started exploring this data about climbing expeditions in the Himalayas. So this is this week's Tidy Tuesday data set, and there's several different data sets that we have access to here. One of them, the data set on the expeditions, on the peaks, but one of them is about the expedition members. So who has actually been on these different expeditions to climb all these different peaks that are here in this peak ID and peak name columns here. So we have expedition ID, member ID, and then we have a lot of interesting data about these people who climbed these mountains in the Himalayas. Things like how old they were when they made the climb, what is their citizenship, did they use oxygen or not, and whether they died or not. So this is a dangerous thing to do, and what we're going to do using this Tidy Tuesday data set this week is build a model to build a model to predict the probability of an expedition member dying or surviving based on other characteristics of the person and the expedition, which is what we have here in this data set. So we have, whether they were going in autumn or spring, what year they did, and then characteristics of the person and whatnot. So this is, so we'll be able to see how well can we predict that. So does the information we have in this data set, is it predictive of whether someone survived or not, was able to survive the climb that they were doing, and then can we learn something from the model that we have? So that is what we're going to do. So let's let's use Skimar to see what we can learn here about the data that we have. And I'm going to do that again and stretch this out this way so we can, I'm going to stretch it out a little more. There we go. I'm really zoomed in here so we can see this a little bit better, because I want to look at so this is how many expedition members we have, the number of columns we have overall, and then let's look at a couple of things here. So we have the IDs for everyone. We don't know actually what names go with the peak ID for a couple of these. We're missing sex or gender for a couple of these. For a few, we're missing citizenship. We're missing expedition role for a little more. These information, it looks like we're not missing at all, and these are these logicals. So hired, so this is was this expedition member one of the people who decided to come and climb the mountain, or is this one of the people who were hired and paid to come along with the expedition? Often these are people, a lot of these folks are people who are native Sherpa climbers, and so this is how, let's see, so about 20% of the people in the data set are these hired people, or maybe the other. So hired false. Yeah, okay. The How many succeeded? So did they actually make it to the top? How many of the people made it to the top? Or how much, I think the success is actually not did the person make it to the top, but did the expedition make it to the top? Was there oxygen used? Was it a solo climb, which is very tiny, and whether the person died? So notice here that that is a very small proportion. So this means this is we're trying to predict something that is not happening very often in the data set. So this is going to really impact the choices that we make throughout modeling, throughout feature engineering, pre-processing, and modeling. We're gonna see how this affects what it is that we can learn. Year. This is the year that the expedition happened. This is the age of the person. That is missing a fair amount. And actually, that's missing so much that we're going to practice, I'm going to show and demonstrate how to use tidy models to do imputation. So two things we're going to look at how to do today are how to handle class imbalance, how to be able to try to build a model that is going to be able to do a good job even though we are predicting something that doesn't happen very often in our data, and then how can we impute missing data, because I would like to see if age makes a difference for whether someone survives or not, but we have a lot of missing data there, and I would really not like to throw away 3,500 data points if I can. And then a lot of this other stuff is missing, so we probably will not use it. So for example, I don't mind, I'm probably going to filter out some of these things that are, that there's only, 2 or 10 or 20 filtered out, or that are NA, that are missing. But we're going to impute that age there. So Skimmer is such a great package to be able to just get a really high level view of what is in your data. And after we do that, we can start to do a little bit more detailed exploratory data analysis to be able to see what's here. First, let's look at year and see how, for example, did the number of people dying, and while we're at it, let's say, did the number of people succeed, or the number of expeditions, number of people and their expeditions change? So let's look at this. All right, so there's a lot of, people didn't go every year there, especially near the beginning. So let's do let's round this to by every decade. So say 10 times, and then let's put a year floor division 10. So this should round. So now we have by decade. So these are the percent of people who died and the percent of people who succeeded by decade. Let's make a little plot of this. So we're going to need to pivot longer, transform this from a wide to a long. So we're going to do those two columns. Those are the ones we're going to pivot and reshape. And let's say names to outcome and values to, let's call it percent, I suppose. And now we can plot this into a plot. So we'll put a year on the x-axis, percent on the y-axis, and let's say color equals outcome like this. And then we'll make a line. I'm going to make it a little bit transparent, a little bit thicker, and let's see what that looks like. Nice. Okay, just to emphasize, I'm not going to spend a ton of time on this plot because I want to keep going, but let's just make the labels show that they're percent format like that. Okay. Nice. Okay, so this shows us over these decades that we have since about the beginning of the 20th century, Looks like success is on its way up. Still not very high. It's still below 50% of the percent of people who were on expeditions who succeeded. I might be interested checking the number of people per expeditions over time. I don't know. And then the percent of people who died. So it looks like it was up and down there a lot back in the day, but then it looks like it's quite safe. I mean, I don't know. That's still way. I would not start a hobby that had that percent of people dying, but it is much lower now than it was in the past, especially in those early decades. So we kind of have success on its way up, death on its way down over time. Sounds good. Yeah. We could do the same thing for age. Let's just change out age here and plot that. Okay, so now this is age. So in terms of who is dying, age does not change much until we get to that older age group. I don't know why there are people that are being rounded down to being infants. Were there really children who go up on these? I don't know. That would be interesting to look into. But if there are people who are 10 or teenagers, that seems a little more reasonable. Anyway, okay, so for the bulk of this, the percent of people who die is about the same until the very oldest group. And the percent of people who succeed by age, though, wow, that's pretty interesting. It really goes down. The younger you are, the more likely you are to be on a expedition that succeeds. It just goes down and down and down, like 20, 40, 60, 80. So the older you are, the less likely you are to be on an expedition that has succeeded. So that's pretty interesting. Okay. So that's success, death, year, age. Let's actually look at success and death. So success, remember, let's do this just to make sure, So success is about whether the expedition succeeded, and died is about whether the individual died. Because it is possible to die and have the expedition succeed. But it looks like proportion-wise, let's check this. Let's see group by success, and then mutate percent equals n divided by sum of n. Okay, so more people died in the failed expeditions than died in the succeeded expeditions. So you would rather be on a successful expedition. You're more likely to survive if you are on a successful expedition that makes it to the top. It is quite low in both, though. Remember, we're dealing with an event that happens rarely. So fortunately, you are most of these expeditions, most of the people who go on these expeditions don't die. It's a rare event, but you can see we do see this difference here, and we're able to look at the counts to understand that a little better. Let's look. This has lots of different mountains. In this, lots of peaks in the Himalayas. So let's see, what do we have here? Peak name. All right, so more people are climbing Mount Everest, but then we have these other Himalayan peaks as well here. There's, boy, just a ton here. So for our model, that's going to be kind of too many to include in the model. So we are probably going to, and if I remember from Skimmer, we have some NAs in this as well. So let's filter to not NA. And then let's use, I'm going to say mutate peak name, and I'm going to use a function from ForCats called fact lump, where I'm going to lump less common ones together. I'm going to call it prop, and I'm going to use a prop so that anything less than 5% is going to go together into an other category, and then I'm going to count peak name and died. So I can see here. All right, so now we're down to 10 categories, which is more reasonable. We have the most, the peaks that have been climbed by the most people, and everything else went into other, which you can see is now the biggest category. And I can't look at that and see that off the top of my head. So we will now group by peak name. And what do we have? All right. It looks like this is a bit high. Monoslu. I should look up how to pronounce that. Monoslu is a bit higher. So some of these have lower numbers of people dying. Everest looks to be higher than some of these other ones, but lower than these others. So we definitely see differences across peak. That will be interesting to see. The last one, maybe we'll check before we get started on the modeling, is season. So let's count season died here. Oh, we've got an unknown. I'm gonna only keep the 4 known seasons. And then I'm going to do the same thing that I did here, this group. And so forth, like this. And then I'm going to make a little visualization, because it looks to me, looks like winter is worse, but it's always nicer to look at a visualization. And I could have done this with any of these, but I'm going to do it here for this last one. So I'm gonna instead of having a logical, let's turn this into a character. So when died is true. So when a person has died on their expedition, I'm going to replace died with the logical vector died with the character died, and all the rest of the time I'm going to say did not die, like so. And then I can make a plot. Let's see, let's put season on the x-axis, percent on the y-axis. Let's fill by season. We're going to make little bars. Let's see, we're going to do show legend equals false. We're going to, I think, need to say position equals dodge here, so they're all next to each other instead of all on top of each other. And I'm going to make them a little bit transparent. And so if I do all this, it's all just, look, it's just all together, right? So what I need to do is I need to facet wrap died like this. They're just on top of each other right now. And I'm going to need to say scales equals free like this. And there we go. Very nice. Oh, the last thing, just because it is scale y continuous labels equals scales percent format, like so that we can look at this. There we go. Okay. So this is, good to see. Most people did not die. But we see a pretty big difference from autumn, spring, summer to winter. So winter is significantly worse than the other seasons. So this again is something that we will definitely want to include in our model. Speaking of which, let's get this ready. Okay, so we've been doing we've just been dealing with that raw data set that we started with, and let's start to think about what we want in the data set that we are going to use. So let's keep out that unknown. So let's see, I'm going to use peak ID instead of peak name. I want to try and see year, season for sure. We didn't look at sex, but let's try sex. We looked at age. Let's try citizenship, like if we see difference between people who have different national citizenship, whether they were hired or not. Success, it really looked like there was a difference there, and died, which is going to be the thing that we are going to predict. So I'm going to filter out those things that we knew were, we have some NAs, but there were only a few of. I'm not going to filter out the ones that are NA for age, because I am going to impute that. There were a lot that were NA there, and I'm going to impute that instead of removing them. And I could impute all of them, but I'm going to show how to just impute the one. I think that would be a better choice in this case, to filter out just the few that are missing a little, and then impute the one that is missing a lot. That's the approach I'm going to take here. I am going to train classification models, and in tidy models, to do that, your outcome needs to be a factor. So I can't have that died be a logical vector, so I'm going to do the same thing here, except let's call this died, and let's call this, that's a little better, survived. I should have, that would have been nicer up there too. Let's change everything to everything that is a character to a factor. And that looks pretty good. So we only filtered out just a handful here. Which is that was the point of only filtering out these things and keeping the age. So let's call that members DF, like so. So this is what we're going to use for our modeling. Let's get started on that. Whoops, that's not what I meant to do. There we go. So let's load tidy models, the meta package that has all the packages we're going to use for modeling here. And the first thing we're going to do is we're going to set a seed, because the first thing we're going to do is an initial split on that members DF, and we are going to do stratified splitting or resampling on that our outcome, because we want it to be balanced in that, especially in this case where it is a pretty rare event. And so we'll say we'll call this members train, and then let's call this members test. All right, so we have, the first thing we do is we split the data that we have, which in this case, fortunately, is quite a good amount, into training and testing. So our training data, has almost 60,000 points, and our testing data, which we are going to set aside and use to evaluate our model at the end to get an estimate for its performance on new data, has about 19,000 rows in it, and they'll be balanced in who survived or not. While we're here splitting data, let's set a seed again. there we go. And let's create a set of resamples. So so first we set training and testing. And then we're going to take that training data and we are going to create a set of cross-validate of what am I doing here? Of cross-validation folds from it. Let's call it members folds. So these are the expedition members. So each one of these is a fold of data, a cross-validation fold, where this is what we have total, and then this is the held out set for this split here for fold 1. And so when we come and we use this resample, we will train on all of the data except this, and then we can evaluate on this. So we can use the resampling to compare models, to we could use it to tune models. So the testing data up here, we're saving for the very end to get an estimate of performance on for the future for new data. But these resampled things, which we created, notice from the training data, we will be able to use to during our whole modeling process to make choices. All right, so the next thing we're going to do, so we took our data, we got it ready, we split, and then we made resamples. The next thing we're going to do is we're going to do feature engineering or data pre-processing. So we are going to explain who died with everything else we have, and the data we're going to use here is the training data. Members train. So let's call this members recipe, like that. And now we're going to start adding steps to our recipe. These are steps that we need to take for the feature engineering we need to do. First, let's talk about imputation. There's different kinds of imputation we can do, like mean imputation, median imputation. We can do K-NN imputation. So what the goal here with imputation is just that I don't want to throw that data away. I'm not adding new information. I'm just using the information that's already there in the data set I'm not, like, nothing magical is happening. I'm just using the information that's already there to tell me what to put in those missing data spots so that I don't have to throw away those observations, which have important, or I think probably valuable information in the rest of it, in not age. So I'm actually just going to take a really simple approach. And I'm just going to use the median to impute that. So what that means is it's going to say, hey, what's the median age in members train, or in the in the data set I have? I'm going to put that into age. You can. There's other options there for imputation, but in this case, we're just going to do something straightforward. I am remembering that some of these things, like, citizenship, I bet. We haven't really looked at that yet. So there's 200 different kinds of citizenship. Remember, there were like 300 or 400 different peaks. That is too many levels. If we try to, train any kind of model, it's not going to be happy when we do that. It's not going to be a good time. It's not going to be a good choice. So what we can do is we can use a function called step other, and so it's going to pool the less frequently occurring values together into an other category, much like we did with fact lump from 4cats. So I'm going to do this for peak ID and for our citizenship. I don't think there's anything else I need to do it for. No, everything else should be okay. And there are there are factor variables here, and I am going to use a model that can't handle factor variables as is. So that means I need to create indicator or dummy variable. So I'm going to say take everything that is a factor or character, everything that's nominal data, and turn it into a dummy variable, except I don't want to do it to my outcome because I still need my outcome as a factor. And then the last thing I believe that I need to do for feature engineering is to handle the class imbalance. So class imbalance is handled. We have a separate package in Tidy Models that holds some extra recipe steps, and there's several different things you can do. We can do things like first of all, we could step down sample, so we could throw away everything that's not we could throw away a lot of people who survived and then have a much smaller data set. I think we're not going to do that this time. Instead, we're going to try to do an upsampling. If you do plain upsampling, what often can happen is that a model will just really memorize the especially like a more powerful machine learning algorithm like a random forest or something will just really memorize the few examples that you have. So instead of step up sample, we're going to try a slightly more sophisticated option. Let's use there's different ones like step B smote, step smote. So let's see, what it does is it uses nearest neighbors. So it's going to try to it's going to make new examples of people who died using nearest neighbors of the examples that we do have. So we want to upsample on the people on the expedition members we have who died, so that we have the same number of people who survived and died. Because right now, for example, members train, we have many more people who survived than died. And for our model, we want that to be balanced so that we can do a better job of learning to recognize both kinds of examples. So let's do this. So right now, we have defined this recipe, but we haven't computed anything. For example, we have not computed the median of age. We have not gone to all the things that are factors and figured out what levels we need to do to make indicator variables. The thing to do that is to prep the recipe. Oh no. It's not happy. Let's see. So member, it wants them all to be numeric. Oh, you know what? It's these logicals. Because they're not factors and they're not numeric. Let's go back up here. So say mutate if is logical. Is logical. And say as integer. So this is going to change them from those true falses. Whoops. Oh, it can't have like that. Okay, so before they were true false and now they're zeros and ones. So now so it's like I made my own little indicator variables effectively by like manually. So let's resample and let's reset up my recipe, and now the recipe is defined, and now if I prep it, it just calculated things like it found the median for age, it found the factor levels, it made indicator or dummy variables for all these, and then it did all these like k nearest neighbors here. If I want to see, I'm like, okay, I did that thing, but what, like, I want to see it. I want to see that data that you found it. So what you do is you bake it, but that data is already in there. So we want to we want to bake it with new data equals null, like this. So we're not passing any new data. I want to say, hey, I don't have new data. Give me the data that you trained on, the original data. And so this is what we get here. So we have, instead of peak ID, notice that we have these peak ID for things like, for, Everest here, for other here, for this one that a lot of people died on. We have, notice we don't have autumn because that's the base level, but we have spring, summer, and winter. We have male, but we don't have female because female was the base level. And yeah, okay, so let's convince ourselves. Okay, so the upsampling worked. So we successfully, we have a lot more rows now because we created new synthetic observations using the SMOTE algorithm here, using step SMOTE. So this is how you can handle the recipe to figure out what's going on. We are going to use workflows for our actual model training because it is easier. And a lot of things get handled easier. So let's try 2 kinds of models. This is actually the same 2 models that I used in the video I did maybe a month ago or so with the Palmer Penguins data set. So it is a simple, or I don't know if simple is the right word, there's a lot going on in it, a basic logistic regression model and a random forest model. So let's make sure there's enough trees, and we're going to use Ranger as the engine, and for a random forest model can be used for either regression or classification. So we need to set it. So now we have these. Now we're saying, here are our models. Here's the models that I have, and now let's set these up to be trained. So let's set the workflow here. So workflow, and then we can add a recipe like so. And this is the recipe that we want. So, and let's call this members workflow like this. Let's take a look at what the workflow looks like right now. Look what it says. So preprocessor recipe, that's the recipe that we added, and model equals none. So a workflow is like, think of it as like ways to stick things together like Legos, and then you can carry it around. And right now there's nothing stuck in the spot for a model. It's like empty right now. The spot for the model is empty. But it's just there waiting for either one of these. So we can go and add the model to it. Let's add the model to it and then keep going and pipe and fit. So we're gonna add a model. Let's do GLM spec, and let's look at what that looks like. So now it has 2 things in it. It has the recipe, because remember I saved this object with the recipe in it, and now it has a model too. So this is now an unfit workflow here. And then we're going to use fit resamples, because we're going to use these resamples we made, or these folds that we made, to fit these 2 models and then see how they did. These are both models that don't need a lot of tuning, because they do they have either they don't have tuning parameters or they do pretty well with their defaults. So we do not need to there's not a strong reason to tune either one of these. So we're just going to use fit resamples, which means we're going to fit to all 10 of those cross-validation folds and then be able to use that empirically to be able to say which model is better. So we're going to say resamples equals members folds. This is what we're fitting to. I am going to set some metrics here. If I didn't do anything, it would compute accuracy and ROC AUC. So let's, I mean, I like those. Let's keep them. ROC AUC, accuracy. But I have a really rare positive, like really rare event. So I want to do sensitivity and specificity here so that I can easily find those. And then I also want to save the predictions because I want to make some plots with the predictions afterwards. So let's use parallel processing because that will make this go much faster. And then let's do this. So what this is doing is it's taking this workflow that has so it's a tidy models workflow. It has the pre-processing recipe, which does imputation, collapsing factor levels, make me indicator variables, do upsampling, and then it fits the logistic regression model. So it did that for each of these folds. So it did that for each of these folds. It did that whole process for each of these folds. So, excellent. That ran pretty fast because logistic regression, we all love it for many reasons, including the fact that it's fast. Random forest is gonna take a minute. So we'll switch out the model specification, but everything else we're just gonna keep the same. And that we're gonna get started. And so what's happening here is that for every fold, that data pre-processing recipe is being executed on it, and then a random forest model is being fit on it, and then it's being evaluated on the held out set in this resample. And then that whole process is being done again here. On the non-held out part of this resample, do the data pre-processing, do the fit the model, evaluate on the held out set. So the reason why we do this kind of resampling is because it helps us, it can give us an empirical measure of being able to compare models. This is going to take a minute, so I am going to pause the video and then come back when it's done. All right, we're back. We have random forest results. That definitely took a minute, and all the fans on my computer ran, but congratulations to my computer for finishing. I'm very proud of it. And now we have results, and it is time to evaluate the models. So we can use the function collect metrics. So the metrics are in these columns here on the results, which are like tables full of lots of delightful things in these tables. But there's a helper function that can help you get those out called collect metrics. So let's do it for both of the kinds of models that we fit, and take a look here. All right, so the random forest accuracy is fantastic. Would you look at that? Wow, fantastic accuracy, so high. The logistic regression much lower. The ROC, AUC, they are much closer to each other, and the logistic regression is only a little bit worse. Now, what is going on? What is happening? We can tell by looking at sensitivity and specificity. So the logistic regression model, those two numbers are kind of close to each other, close-ish to each other. And so the logistic regression model didn't do so bad if you compare how did it do for the positive and the negative cases. Those are not fantastic numbers. Don't get me wrong. Like that's not that's not anything to like sing, like write a paper about, or be like, wow, I just can't, go sing a song about or anything. But the logistic regression model did about the same for positive and negative cases. It was about equally able to recognize positive and negative cases. What about the random forest? We cannot say the same. It has a very hard time finding the minority case, finding the people who died. We can find this, see this in a little more detail with this with a confusion matrix. So this is the truth. So and this is a logistic regression. People who did die and were predicted to die is about twice as big as those who were predicted wrong. So about 2/3 of the people who died were predicted correctly, which is, why we're right around to the 2/3 number here. There we go. This is why this number is 2/3. It's because, it's about 2/3 here. And then did a little bit worse on the people who survived. What about if we change it to the random forest? Okay, so these are the people who died who were correctly predicted to have died. These are the people who died who were predicted to have survived. It was very hard for the random forest to predict this. Even when we really took out all the stops and tried the SMOTE algorithm and all this kind of thing, we were not able to build something that the random forest was able to recognize the minority class very well. So if we wanted to use random forest, we would really need to look into another option here. For us here, we're going to say that the logistic regression did better, and we're going to move on. So we're going to get out the predictions, and then we can group by ID. Let's remind me what it looks like here. So we have this ID, which is the fold, and then here are all the predictions for everything that was in there. So if we group by ID, we can do an ROC curve, make an ROC curve, and it would be died, the real truth, and then the probability, the predicted probability that they died. So we have 10 ROC curves here, and we can pipe this to auto plot here. And so this is the auto plot. This is the ROC curve, or 10 ROC curves actually, for the logistic regression model. Let's show you. Let's look at what the random forest model looks like here, and let's make this a little bigger. And let's switch back and forth. So this is random forest. This is, wait, which one is which now? Okay, now I've got them confused in my head. Okay, so random forest is here. Logistic regression is here. So the differences that we see are related to those to the differences in the sensitivity and specificity, and how those cutoffs would work. Okay, so we're going to use the logistic regression model. So we decided we're going to use it. Right now, it's been trained on resamples, but has not yet been trained on all the training data. So let's do that right now. So we can take that workflow that, remember, is kind of an incomplete workflow here, and we would need to add the model again, the model specification, and then we could fit to members train, and then predict on the test set, but there's a nice little helper function called LastFit, and we fit on members split like this. And what this does is it fits on the training set, and it evaluates on the test set. So it's just like a convenience function for the thing we usually do at the end of a modeling workflow, modeling analysis, which is to fit on training data, evaluate on testing data. So if I do collect metrics on members final, this thing that I just made, these metrics are on the testing data. So they are, let's see, they are a little bit worse, not hugely, a little bit worse. So maybe we've had a little, I don't know how big were the standard errors. Maybe a little bit worse. And we can also collect the predictions on members final. Notice the number of them. This is the testing data. This is the first time we've used the testing data, this whole video, this whole analysis. And we can do a confusion matrix on this as well. Confusion matrix, and it would be the same as, it would be died, predicted, class, like this. Okay, and so this is the truth up here. So this many people of who actually died, this many people were correctly predicted, incorrectly predicted. So correctly predicted, incorrectly predicted. Notice that the testing data has not been has not been oversampled. Whenever you evaluate on testing data, you do that with the like it's real life in terms of what the sampling is. All right, and so this members final object, if you were like, okay, I did it, I need to save this object to use in the future when I renew data, you could save that whole members final object as like an RDS or something like that, or you could pull the workflow. It's like, I don't know. We should maybe, I don't know about that. We gotta pluck it out. It's like in a list. And then we can tidy. In this case, it is just a linear model, so we can tidy it like this. This is pretty interesting. Let's exponentiate it. Exponentiate equals true, so that we get, now we have odds ratios. And let's cable digits equals 3. Nice. You know what? I'm going to add one more thing. A range estimate. Like this. So we can see, okay. So these things down here on this side are the things that increase your probability of surviving. So going on a trip in the summer, being on an expedition that succeeds, being a UK or US citizen. This is getting to be pretty small, but going later, don't go in the year 1910. And then these things down here are things that make your probability of dying higher, of surviving lower. So these peaks like Everest or other, remember how many of those? There were a lot more people who died on those. Being one of the hired people on the expeditions, being a man compared to being a woman, being a citizen of Nepal. So we see here this evidence that these, and this is something there's been a fair amount of press and writing about is that that this is actually a job for native Nepalese Sherpa people, and that this is actually dangerous. And so we see here that it actually is more dangerous for these hired, like on a per expedition basis, it's like more dangerous for those folks. It looks like from this model at least, than from people who come in from elsewhere, which is pretty interesting. Let's see. Let's make a little. Let's make a plot. Let's not put it on that scale anymore. Let's put it back on the other scale, and let's say estimate, fact, reorder, term, estimate, and we're gonna put some points. All right, let's take out the intercept. Because that's not so helpful for us. And then let's put on those error bars. Error bar. And we're going to say x min. So it's estimate minus standard error. X max equals estimate plus standard error. I think that's all. Let's see what we got. Nice. Why does it always look like that? And let's put, before we start putting any of this down, let's put a horizontal or a vertical line at 0 and make it dashed. Like so. Nice. Okay. Let's call this the end. Let's look at this. Ooh, re-render. There we go. Okay. All right. So these are, so what's on the, what is on this axis? This axis, this is the coefficient from the logistic regression. So we didn't exponentiate it. So it's back on that, back on the other scale. So the things over here on the positive side are things that increase your likelihood of surviving. The things over here on the negative side are the things that increase your likelihood of dying. And we can see, and we kept everything pretty much on its real scale. We didn't normalize things because we didn't need to for these models. So this is like citizenship of USA versus whatever the base level was. I don't know, like Australian or something with an A, I forget. Well, we'd have to look that up. So did it succeed versus not? Like it increases the coefficient is this big. Summer versus autumn. Summer's way over here, really helps you. Winter is down this way. These peaks over here down this way, they really increase your likelihood of dying. So so we're able to get this out. So this, the things that I'm saying right now are like interpretive, like why, what's going on. But it is important to keep in mind how closely did this model fit the data, which is what we were measuring when we were looking at the accuracy numbers. And so remember that this we was definitely better than we were able to see some meaningful fit to the data. This is better than guessing, but this model does not fit extremely well. We're not able to predict with high accuracy. We are able to predict with, let's call it medium to low accuracy. And that's probably why the random forest model did so poorly, is because the data that is in here, the information, the predictive power that is in this data isn't enough to predict whether someone will die or not. Like just these handful of variables isn't enough to really predict that with high accuracy. So we're able to learn about some differences, but not build a super highly predictive model, such like the kind that a random forest would be able to really take advantage of.
Okay, we did it. We used tidy models to train models to predict who survived these climbing expeditions in the Himalayas and who did not. We were able to achieve, like medium predictive accuracy, which we use that information in being able to interpret the results, like how much information is there in what we know about who survives and who doesn't. We were able to learn things about what season are people more likely to die versus survive. We're able to see in these results a little bit of information about what a dangerous occupation this is for people who are hired, and we saw that even reflected in the citizenship data. We saw people who were native peoples there in Nepal, like such as the Sherpa people who are hired to go along on these expeditions, were more likely to die compared to people of other citizens. So I think this was a really interesting data set to be able to practice some of our skills, like building models, imputing missing data, being able to account for the class imbalance, because dying, fortunately, is rare compared to surviving. And I hope this was helpful, and I'll see you next time.